Good morning. Good morning. Welcome to lecture number 8 in our little course, Introduction to Statistics. Now I'm having a little pre-election, US election here. You can join in if you want. There must be some Romneys out there. Anyway, this is the type of data, the type of situation we'll be looking at next time. Like my little newspaper story with the lazy students who do not prepare for teaching at university. So look at that for next time. And join the party here. Are we okay, Georgia? Now we're okay? Okay. So, today we are going to do something else. I will start today by looking at this terrible or nice, depending on how you look at it, table 8.1. That will serve as a kind of repetition of what we have done the last couple of weeks, 2 or 3 weeks. That is somehow collected, all the main part of what we have learned of principles and methods. You can see we learn some thinking and some principles, some abstraction in this course, and we learn some specific methods to apply for specific situations. Let's have a look. Let's start to zoom in a little bit. Now we can still see the whole table. I'll zoom more in a little while. It tells us that it's a summary of formulas for inference about the mean or the difference of two means. That's what we have been discussing the last couple of weeks, 3 weeks. Basically, we were given two methods. I mean, two sort of type of methods: the confidence interval and the test statistic. That is the hypothesis testing, right? That's the two methodologies that we are gonna use for doing what is known as statistical inference. Inference is the generic word for what we do, trying to say something about the world, the population, based on some sample data. Now, the confidence interval, always, as we've seen it so far, when it has to do with means or difference of means, comes as a point estimator plus minus some value, that is a t or a set coming from a table, times some kind of standard deviation from the sampling distribution, right? The test statistic is also always, in all cases we've seen, given by the point estimator. That is the word for using the data. The point estimator is the data value. When we test hypothesis, we compare the data with what the null hypothesis is claiming, and we take this difference relative to the sort of the variability of what we are looking at, the noise, the uncertainty, and this is what is in the denominator here, the standard deviation of the point estimator. So it's the same sort of building stones. Then we have seen 3 different situations, and that's what we see in the table. We could put some vertical lines in the table like this. Then we have seen, we started out with a single sample situation. Then last time we took 2 independent samples, and also last time at the end, the sort of the matched pair situation. 2 samples that were matched or paired, you could say. That was the 3 different situations that we have met, and they are all summarized in the table here. Let's begin with a single sample. Should I zoom in a little bit now? a little bit more. I'd like still, I mean, the nice thing of the table is to have the overview, so it's difficult to have the overview and zoom in at the same time, but still, I think here it's somewhat readable, although a bit small, but still readable for most people. In the single sample, we were either in what was termed the general situation. That actually refers to the sample size that we are assuming here. We assume here a large sample size. Or you could say the other situation, we do not assume a large sample size. N could be anything from 2 and up. 1 doesn't really make much sense. So from 2 and up, when we are in the other situation with a small sample here, we actually assume, it's said here, the normal. So we actually have to make a formal assumption about the population or the situation at hand that it actually can be described by a normal distribution. So that is a non-trivial assumption that we do. Now, the variance of the point estimator, I mean the point estimator is just the average, right? No difference there. The variance and the estimated variance, you could say, or rather the estimated standard deviation, the one that enters into the formulas up here, would be S over root n in both cases. Then, if we have large samples, we can use the normal distribution. Here it says what distribution should we use in the case. We should use the normal. If we have a small sample size, I mean, the funny thing is we have a small sample size. We assume that the situation actually, that the original x can be described by a normal distribution actually. Then the theory comes up and tells us don't use the normal anymore. Use the t. The t is a version of the normal with a bit more uncertainty. That is a bit heavier tails. That's one way of saying it. And the test statistic, you can see, I mean, the two columns here are basically equal. The only difference comes from the assumption and from the distribution that we should use. The test statistic is the one t-test statistic, as you have seen previously. So that was very detailed summarizing the one sample situation that we did a few weeks ago, actually. Can you see we have a problem here? Or maybe a problem. What if we have a small sample size and we do not dare to assume that the situation is a normal situation? I mean, there are many, you could say, things out there that does not behave like a normal. And what if we would like to do statistics in a case where the things do not behave like a normal and we still only have a small sample size? Then this table does not provide a solution for us. Then what we have learned so far does not give us a solution to what we can do. We will mend that in 2 weeks from now, right? So I'll give you methods for that situation also. The methods in the book so far only applies either if we can assume that the normal distribution works in the outset, such that if we plot the original data, they should look like a normal, or if we have a large sample size to put the CLT, the central limit theorem, in play to rescue us, such that the sampling distribution still becomes a normal, even though the original one doesn't. If n is not large enough, CLT will not save us. CLT, central limit theorem, will only save us for a large enough n, right? But the methods will be there. It's just to say these are the classical assumptions for classical statistics that most people apply and use, but we can also do statistics even though they're not there. And I'll teach you in 2 weeks. Now, I'll be a bit faster now running through the table. Now we have the two independent samples. We could emphasize that it's two independent samples that we have learned so far. Actually, it's put into 3 situations, 2 of which we have discussed, 1 of which we have not discussed so far, so actually it's a bit twisting, sort of to call it a repetition, but it was a plan that now was the time to tell you. Let's look at the 2 that we have studied explicitly. The one which is called general, that is the one assuming that we have large sample sizes. When we have large sample sizes, what we do when we do test statistics, or using also for confidence intervals, what we do is to plug in the 2 different variances as they come. We compute one variance, we compute the other variance in the 2 samples. We plug them in the formula and we move on from that. Now, the other situation that we've been facing and discussing and using and looking at is the situation where we do not assume large sample sizes. I mean, this assumption that the both ends are above 2, that's almost the same as having no assumption, right? It's just as of 2, that's almost nothing. However, then we have to assume to apply what I told you last time, that's what I taught you last time. Then we go ahead and combine the variance information from the 2 groups into this pooled variance. We pool them together. That's why we use P as P squared. And then we use this joint, this average, or sometimes weighted average variance. We use that in the formulas for computing things here. And we use a t distribution with n plus n1 plus 1, n1 plus n2 minus 2 degrees of freedom. Now, these were the 2 things I sort of explicitly told you. What we also see, actually, what we saw maybe was that the t-test function in R, and we'll get back to that, actually by default was spitting out something else. If you remember, I had to put this option var.equals true. I had to specify this option. If you don't remember it, I'll tell you now. I had to specify this option in the test, in the t-test of R, to have it give this one to me, right? To give this one to me where I assume that the variances in the 2 groups are the same. By default, which actually makes quite good sense, by default, R does not make that assumption. And of course, that is more safe, not making an assumption. What R then actually enters is something differently, and that I didn't give you the explicit formula for that. Actually, the formula for the t-test statistic is not something new. The formula for the t-test in such a case would just be plugging in exactly like this one, right? It's just like the one to the right. I just plug in the 2 different variances in the formula, like for the large sample size situation, but now for small sample sizes. I plug in these ones. However, then the theory, the probability theory underlying this is actually becoming a bit more complicated. I do have some additional math lectures on that on the website if you're interested. I mean, and if you really want to learn it, you have to take the probability course. Then you will learn it. I give you some small sort of sketches of how you can prove this if you want to dig into the math and the probability theory. It's a nice theory, but it's not part of this course. As it says here, you should use the t, but you should compute the degrees of freedom by this nice formula. This is the footnote of the course. If you look into it, I'll tell you, I've never made an exam question making people have to remember this footnote. But I'm warning about it each year, each time. And eventually, I'll do it, right? Eventually, when I'm having a bad day, doing the exams for you, when the mood is not up on a 5, I'll do it. I just warn you. I mean, if the mood is 5, I don't do it. But if I'm having a bad day, I know myself well enough, then I'll do it. I'm sorry, that's a confession. That's how I am. I didn't do it yet. I wasn't, life is good to me, so I had no reason not to be in a good mood. But you never know what life brings, right? So, one day I'll do it. But then, of course, now I told you, so you know. It's not very complicated. R does it by... Actually, the formula looks terrible, but if you look at it, it's just the standard deviations and the ends. So it's not a complicated thing. It's just plugging in S1 and S2 and the N1 and N2. And then you get some degrees of freedom, which typically always will be less than the other one. So that's the footnote of the course. Finally, in the table, and we could we could almost not, we could avoid this, but actually still the match pair or the pair t-test is so well known by its own right that we call it and give it its own column, because actually we could, since the paired situation, we were taught that we should handle the paired situation by subtracting the data from each other, and in that way actually making the two-sample paired situation into a one-sample situation. And having done that, we wouldn't actually need a column in the table. We could just reuse the single-sample columns, actually, and then only actually one of the two columns are stated here, namely the one where I do not assume large samples, but just assume. So basically, this column here resembles, I have to make it right, this one, right? Assuming small samples, or not assuming large samples. Have people been thrown out, or is it just new people coming in?
No, it's a Flash plugin.
Okay, bugger. But the people are up and running again?
Yeah.
Basically, it says the same thing as over here, that we look at the differences, we compute the average difference, we use this standard deviation divided by root n, we use the t distribution with n minus 1, and we do the t-test statistic exactly like here. So basically, that's it, that's what we were taught last time. Let me focus on the final thing here to move on to the topic of today. Please note that one of the things that was important or could be important for the proper choice of which t-test statistic we should actually use in the independent sample, two-sample situation was and is whether the variances in the two groups could be assumed to be the same or not. If they can, it makes sense to pool them together, and that's actually better. If it's okay, it's better. If it's not okay, we shouldn't do it. But how could we know whether it's really okay to put the variances together? For that, actually, it is important for us to be able to look and make statistics, do inference on the variances themselves. That is also important. That is important for this, and it's important for even more general applications. And that is, in fact, the topic of today. So we start with the first